Motion in a straight line. Introduction. Motion is common to everything in the universe. We talk, run, and ride a bicycle. Even when we are sleeping, air moves into and out of our lungs, and blood flows in arteries and veins. We see leaves falling from trees and water flowing down a dam. Automobiles and planes carry people from one place to the other. The earth rotates once every 24 hours and revolves round the sun once in a year. The sun itself is in a motion in the Milky Way, which is again moving within its local group of galaxies. Motion is change in position of an object with time. How does the position change with time? In this chapter, we shall learn how to describe motion. For this, we develop the concept of velocity and acceleration. We shall confine ourselves to the study of motion of objects along a straight line, also known as rectilinear motion. For the case of rectilinear motion with uniform acceleration, a set of simple equations can be obtained. Finally, to understand the relative nature of motion, we introduce the concept of relative velocity. In our discussions, we shall treat the objects in motion as point objects. The approximation is valid so far as the size of the object is much smaller than the distance it moves in a reasonable duration of time. In a good number of situations in real life, the size of objects can be neglected and they can be considered as point-like objects without much error. In kinematics, we study ways to describe motion without going into the causes of motion. What causes motion described in this chapter and next chapter forms the subject matter of chapter 4. The average velocity tells us how fast an object has been moving over a given time interval, but does not tell us how fast it moves at different instants of time during that interval. For this, we define instantaneous velocity or simply velocity v at an instant time. The velocity at an instant is defined as the limit of the average velocity as the time interval delta t becomes infinitesimally small. In other words, where the symbol stands for the operation of taking of the quantity on its right. In the language of calculus, the quantity of the right hand side of equation 2.1a is the differential coefficient of x with respect to t and is denoted by the dx by dt. It is the rate of change of position with respect to time at that instant. We can use equation 2.1a for obtaining the value of velocity at an instant either graphically or numerically. Suppose that we want to obtain graphically the value velocity at time t is equal to 4s for the motion of the car represented in figure 2.1 calculation. Let us take delta t is equal to 2s centered at t is equal to 4s. Then by the definition of the average velocity, the slope of line p1 and p2 gives the value of average velocity over the interval 3 second to 5 second. Now we decrease the value of the delta t from 2 second to 3 second. Then line p1 p2 become q1 q2 and its slope gives the value of the average velocity on the interval 3.5 second to 4.5 second. In the limit delta t tends to 4. The line of p1 p2 becomes tangent to the position time curve at the point P and the velocity t at t is equal to 4s is given by the slope of tangent that point. It is difficult to show the process graphically, but if we use numerical method to obtain the value of the velocity, the minimum of the limiting process becomes clear. The velocity of an object in general changes during the course of motion. How to describe this change? Should it describe as the rate of change in velocity with the distance or with time. This was a problem even in Galileo's time. It was first thought that this change could be described by the rate of change in velocity with time, but through his studies of motion of freely falling objects and motion of objects on an inclined plane, Galileo concluded that the rate of change of velocity with time is a constant of motion for all objects in free fall. On the other hand, the change in velocity with distance is not constant. It decreases with the increasing distance of fall. This led to the concept of acceleration as the rate of change of velocity with time. The average acceleration a bar over the over a time interval is defined as the change of velocity divided by the time interval a bar v equal to v2 minus v1 oblique t2 minus t1, that is delta v upon delta t, where v2 and v1 are the instantaneous velocities or simply velocities at time t2 and t1. It is the average change of velocity per unit time. The SI unit of acceleration is meter per second square. On a plot of velocity versus time, the average acceleration is the slope of a straight line connecting the points corresponding to v2 t2 and v1 t1. Center of gravity. Many of you may have the expertise of balancing your notebook on the tip of a finger.